In today's class, we discuss about compact metric space. Let XD be any metric space and A alpha such that alpha belongs to lambda be a collection of non-empty subsets of X. Now this collection is called a cover of X if union of A alpha gives X. If this is true, then we call the collection is a cover of the metric space X. Now, if in the cover each sets is open, then this cover is called an open cover. Now, if in this cover the number of sets are countable, then the cover is called countable cover. Again, if in this cover the number of sets are finite, then the cover is called a finite cover. Now let Y is a subset of X. Now this collection is called a cover of Y, then Y must contain in the union of A alpha. Now let Xi be the collection, Xi is the collection, and Xi dash be any subcollection of Xi. Now if Xi dash also covers X, then Xi dash is called a subcover of the cover Xi. Okay. Next, Lindelof space. A metric space XD is called a Lindelof space if every open cover of X has a countable subcover. So Lindelof space means a metric space XD is called a Lindelof space if every open cover of X has a countable subcover. Next, Lindelof covering theorem. In the statement is in the real line R, every open cover of a set has a countable subcover. Every open cover of a set has a countable subcover. Every open cover of a set has a countable subcover. Now let A be any subset of R and Xi equal to A alpha such that alpha belongs to lambda be an open cover of A, that is A subset of A alpha union alpha belongs to lambda. Now let A be an arbitrary element of capital A, then A must belongs to the union. That means there exists at least one alpha such that A belongs to A alpha, where A alpha is open in R. Now we know that every open set in R is either an open interval or union of open intervals. So therefore there exists an open interval xy such that A belongs to xy subset of A alpha, where x and y both are real numbers. Now we know that Q, set of rational number Q, is dense in R. Therefore for the real number x and y, there exists two rational number x dashed and y dashed that satisfy x less than equal x dashed less than a less than y dashed less than equal y. That is A also belongs to x dashed y dashed subset of A alpha. Now since small a is arbitrary element of A, therefore we can say that every element of capital A contained in an open interval whose endpoints are rational. Now the set of rational number is enumerable and the product of Cartesian product of two rational product of two enumerable set is also enumerable. Then the set of all open intervals of the form this is enumerable, since A can be covered by open intervals whose endpoints are rational. Therefore, A has an open cover whose every member are open interval having endpoints are rational. Therefore, this open cover must have a countable subcover, and that is Lindelof covering theorem. Now, next one, compact metric space. A metric space XD is called compact if every open cover of a set or the metric space has a finite subcover. So XD is the metric space. XD is compact, means every open cover of X must have a finite subcover. And Heine-Borel property means a metric space XD is said to satisfy Heine-Borel property if every open cover of X has a finite subcover. This indicates that Heine-Borel property and compact metric space are synonymous, because compact means a metric space is called compact if every open cover of X has a finite subcover. Similarly, metric space satisfies Heine-Borel property means every open cover of X has a finite subcover. So both are equivalent, both are synonymous. Now, next theorem, let XD be a compact metric space. And F be a closed set in X. Then prove that F is compact. Now, first, let A alpha such that alpha belongs to lambda be an open cover of F. We have to prove F is compact. That means this open cover must have a finite subcover. So we can write F subset of union A alpha, alpha belongs to lambda, or F union F complement subset of union A alpha, union F complement, and that gives X. So X subset of, or that is equals to union A alpha, union F complement. This indicates that collection A alpha such that alpha belongs to lambda and F complement, this forms an open cover of X. This is an open cover of X. Now it is given that X is compact. Now X compact means this open cover must have a finite subcover. So there exists a finite subcover A alpha 1, A alpha 2, continue A alpha n and F complement that covers X. So X equals to union I from 1 to n A alpha I union F complement. Okay, then F subset of union I from 1 to n A alpha I, that is A alpha 1, A alpha 2, A alpha n is a finite subcover of that open cover. So the open cover has a finite subcover, so F is compact. Okay, now next theorem, let XD be a metric space and F be compact. Then prove that F is closed. In the previous theorem, we assumed that the metric space is compact and F be a closed subset, then F is compact. In this theorem, we assume that XD is a metric space. F is compact, then prove that F is closed. Now closed means its complement is open. So if we have to prove F complement is open, that is every point of F complement is the interior point of F complement. So we choose a point A from F complement. Then for all x belongs to F, d of xa greater than 0. We choose d of xa equals to 2rx where r greater than 0. Then S Rxa intersection S Rx x is phi. Now consider a collection S Rx x such that x belongs to F, because for each x of F we get the open sphere. So collection of this open sphere must cover F, and as F is compact, this open cover must have a finite subcover. So we consider S Rx1 x1, S Rx2 x2, S Rxn xn. That is an open cover of F. Next, A suffix A, that equals to intersection of S Rx1 A I from 1 to n. Then we know that finite intersection of open sets is open. So A alpha is an open set containing A. A alpha is open containing A. Now from 1, S Ri A intersection S Ri Xi is phi. Therefore AA intersection S Ri Xi is phi. This is true for all I varies from 1 to up to n. Therefore AA intersection F equals to phi. So AA, that subset of F complement. Now AA is the open set containing A. That means A is the interior point of F complement. Since A is arbitrary, so F complement is open, that is A is closed. Now the last theorem statement is XD is a compact metric space. If F is closed, then F is compact. In this theorem we say that XD is any metric space, may not be compact. If F is compact, then F is closed. So if we merge the two theorem, we can state that let XD be a compact metric space. If F is compact, then F is closed, and conversely. That is, if XD is a compact metric space, then F is compact if and only if F is closed. Now next theorem, let XD be a compact metric space, XD be any metric space. If F is compact, then F is bounded. Next theorem is that XD be any metric space if F is compact, then F is bounded. So we consider S1x such that x belongs to F, an open cover of F, because open sphere exists for each element of F. So that must be an open cover of F. F is compact, so this open cover must have a finite subcover. So we consider S1 x1, S1 x2, S1 xn that covers F. Clear? Okay. Now let capital M equals to max of d of xi xj, where I not equal j and ij varies from 1 to n. Then for all xy belongs to F, we have d of xy. Okay, if we choose for all any xy, if x and y be any two member of F, then x and y must belongs to this type of open sphere. So for x, the open sphere may be S1 xp, and for y, the open sphere may be S1 xk. Therefore d of xp x less than 1 and d of xk y less than 1. Now for all xy belongs to f, d of xy that less than equal by triangle law d of x xp plus d of xp xk plus d of xk y, that is less than 1 plus 1 2 plus m for all xy belongs to f. That means the diameter of the set f is bounded by m plus 2. So set f is bounded. So compact indicates bounded. In the last theorem we stated that compact indicates closed. So compact means closed and bounded. Now next, Heine-Borel theorem. Heine-Borel theorem is that this is for Rn. In Rn, every closed and bounded set is compact. Previous theorem is compact means closed and bounded. That is true for any type of matrix space. But now Heine-Borel theorem says that for Rn, if n is 1 we get R, if n is 2 we get R square, that is R square Rn. This type of sets or this type of matrix space, every closed and bounded set is compact. Okay, so let S be closed and bounded subset of Rn. Closed and bounded subset of Rn, we have to prove S is compact. So let A alpha such that alpha belongs to lambda be an open cover of S. Now by Lindelof covering theorem is valid for R as well as for Rn. So by Lindelof covering theorem, this cover must have a countable subcover. So we write AI such that I belongs to N. Now we prove that this cover must have a finite subcover. Now we assume that the set is not compact. Not compact means this cover cannot have a finite subcover. Therefore, S minus union m from 1 to p am is non-empty for all p belongs to n, because S cannot be covered by finite number of members. So if we consider finite number of members, p may be any natural number, then their difference is not empty. If difference is empty, that indicates that S can be covered by finite number of members. We call it, this is Bp. So Bp is not equal 5, and it is clear that Bp plus 1 is subset of Bp. That means this is true for all p. So Bp is contained in one another, that is, it is nested. Okay, now each AI is open, so union of AI is open. So S minus this one, as S is closed, so S minus the complement, that must be closed. So Bp is closed. So we get Bp is a collection of closed sets and they are nested. So by nested interval theorem, intersection Bp, p belongs to n, is non-empty and it contains exactly one point, say x. Now as x belongs to intersection Bp, that indicates x belongs to Bp for all p. That indicates x belongs to S, that is equation 1. Now again, x belongs to intersection Bp for all p belongs to n, that indicates x does not belongs to union m from 1 to p am for all p belongs to n. So this is true for every natural number. That means x does not belongs to union am where m from 1 to infinity, because this is true for every natural number. And this already know that this already covers s. So x does not belongs to s, equation 2. So 1 and 2 contradicts each other. And why this contradiction arise? Because we consider s is not compact. So s must be compact. So in Rn, every closed and bounded set is compact, and in any metric space, compact indicates closed and bounded. Now next definition is finite intersection property. Finite intersection property says that if we consider a collection A alpha such that alpha belongs to lambda, be any subsets, be the collection of subsets of metric space, and if we say that this collection satisfies finite intersection property, then we say that every finite subcollection, every finite subcollection of this collection have non-empty intersection, that is intersection A alpha such that alpha belongs to some finite set must be non-empty. Every finite subcollection has non-empty intersection. Now theorem related, that is theorem on finite intersection property. The theorem says that a metric space XD is compact if and only if there exists a collection of closed subsets of X having finite intersection property has non-empty intersection. That means if this collection be a collection of closed subsets and if it satisfies finite intersection property, that means every finite subcollection has non-empty intersection, then the whole intersection must be non-empty. Okay, first proof, let XD is compact. First we assume that XD is compact, and it is given that finite intersection of this collection is non-empty, and we have to prove this intersection A alpha such that alpha belongs to lambda must be non-empty. We have to prove that. Now we start from that. Let intersection A alpha belongs to lambda is empty if possible. Then its complement intersection A alpha such that alpha belongs to lambda complement equals to X. So union A alpha complement is X. Now if A alpha is closed, so A alpha complement is open. So union of open sets gives X, means this collection A alpha complement such that alpha belongs to lambda is an open cover of X. Now X is compact, so this open cover must have a finite subcover. So X can also be expressed as I from 1 to n A alpha I. Now if we take again complement, then phi equals to intersection I from 1 to n A alpha I complement, that is A alpha I. That indicates that this collection has a finite subcollection whose intersection is empty. This contradicts the given assumption. And why the contradiction arises? Because we consider the whole intersection is empty. So whole intersection must be non-empty. That is first part. Now converse part. Now in the converse part, we assume that every collection of closed sets, every collection, mention that every collection of closed sets that satisfies finite intersection property must have non-empty intersection. Now we prove that XD is compact. So we consider an open cover of X. Now we prove that this open cover must have a finite subcover. So X equals to union alpha belongs to lambda F alpha. Now its complement, that is phi, equals to intersection F alpha complement. Now as F alpha is open, F alpha complement is closed. So intersection of F alpha complement gives phi. That means the collection have empty intersection. That means it cannot satisfy finite intersection property. So therefore there exist finite subsets whose intersection is empty. So if we take complement, then union I from 1 to n F alpha I, that equals to X. So this open cover has a finite subcover, so XD is compact. Now next theorem, this is very important. Let XD and Y row be two metric spaces, XD and Y row be two metric spaces, and F from X to Y be continuous. Now if X is compact, then prove that F of X is compact. That is, continuous image of a compact set is compact. Now we first prove that. First consider A alpha such that alpha belongs to lambda, be an open cover of Fx. So Fx subset of union A alpha such that alpha belongs to lambda. We have to prove that this open cover must have a finite subcover. Now we know that X subset of F inverse Fx. So that is a subset of F inverse union A alpha such that alpha belongs to lambda. Now that equals to union F inverse A alpha. Now F inverse A alpha is a subset of Y, and F from X to Y is continuous. So as A alpha is open, F inverse A alpha is also open in X, and collection of open sets covers X. That means F inverse A alpha such that alpha belongs to lambda covers X. Now X is compact, so this open cover must have a finite subcover. So F inverse A alpha 1, F inverse A alpha 2, in that fashion F inverse A alpha n, that covers X. So we say that X equals to union I from 1 to n F inverse A alpha I. So Fx that equals to a subset of union I from 1 to n A alpha I. That means Fx can be covered by finite number of elements, so Fx is compact. So continuous image of a compact metric space is compact. Now next theorem, let XD and y row be metric spaces and f from x to y be a continuous mapping. Now if x is compact, then f is uniformly continuous. Now we have to prove f is uniformly continuous, and it is given that x is compact. F is continuous, so we say that for any epsilon greater than 0, there exists a delta greater than 0 such that d of x c, c is any point of the metric space x, that less than delta implies rho of fx fc less than epsilon, or x belongs to S delta c, that implies rho of fx fc less than epsilon. Now consider the collection of this type of open sphere. C belongs to X, that covers X because we choose each C. So this is an open cover of X. X is compact, so this open cover must have a countable subcover. So we say that S delta 1 x1, S delta 2 x2, S delta n xn, that is an open cover of X. So X equals to union I from 1 to n S delta I xi. Then for any 2 points x and y belongs to capital X, for any 2 points x and y belongs to capital X, we say that x belongs to S, say delta k xk, and y belongs to S delta p xp, because p and k both lies between 1 and n. And if we choose delta means the max of all this thing, then d of x xk less than delta k less than delta, because delta is the max of all this thing, and d of y xp less than delta p less than delta. So then d of xy less than equal d of x xk plus d of xk xp plus d of xp y, that is that less than 2 delta, because delta plus delta 2 delta plus d of xk xp, and d of xk xp is a finite real number because x is compact, and compact means closed and bounded. So d of xy less than 2, say delta dashed, that implies rho of fx fy, Now d of xxk less than delta k, that indicates as it is continuous, rho of fxk, rho of fxk less than epsilon plus rho of fxk fxp plus rho of fxp fy. This is less than epsilon, this is less than epsilon, so less than 2 epsilon plus a finite number. So we say that rho of fx fy less than epsilon dashed. So d of xy less than delta implies rho of fx fxy less than epsilon for any x and y in x. That indicates f is uniformly continuous. ঠিক আছে, আজকে এই পর্যন্ত থাক। আমরা নেক্সট ক্লাসে এরপর থেকে স্টার্ট করবো। এগুলো পড়ো, যদি কোনো ডাউট হয় আমাকে বলবেন।